All right, guys, so in this next video, second to last video of the unit, we're going to be looking at some applications of exponential functions. So this is kind of like part one of this objective number 9. So apply knowledge of exponential, not log, sorry, my bad, functions to real world situations. We are not in this video going to be looking at the compound interest. We're going to be looking at just growth and decay and some like scientific applications of it in part 2 of this, or in the very last video is when we will be looking at compound interest. So if you can join me and go ahead and look at this page right here, which is too much going on. Science, it says exponential functions, science applications at the very top. Sorry for the page numbers loss. So in this, we're looking at bacteria. It's in a controlled colony is found to double every minute. If there is initially, so the starting 300 bacteria, so it's like the initial, right? So at 0, 300, we can think. I'll write down that point. In how many minutes will there be 1 million? Right, so you're trying to find the x value. So let's actually go ahead. Let's think about the variable. So x, or your independent variable, is actually going to be the number of minutes, right? And then your y value, or your dependent variable, is going to be the number of bacteria. So let's think about this. So if you're starting, I mean, we actually have the equation. Y equals your starting value is going to be 300. Your growth rate is double, so that's going to be times 2 to the power of x. So what we're going to go ahead and do is we want to figure out, well, when y is 1 million, right? So if you have 1 million, I'm going to mess this up. It's 100,000. There, 1 million equals 300 times 2 to the power of x. We're going to go ahead and solve it. We're going to use our calculators because we have not learned about log functions, but this is something that we're going to circle back to when we do learn about log functions to see like a different method or way of actually coming up with this. So I'm going to go ahead and divide both sides by 300. I'll get rid of these zeros. So I'm really doing 1, 2, 3, 4. I'm really doing 10,000 divided by 3. I'm going to use my calculator. Divided by 3. I get that really nice number. So maybe I don't want to round it right now. Maybe I'll leave that. So I've got 10,000 thirds equals 2 to the power of x. And I want to figure out where those two intersect so that we can figure out what x is. So I'm actually going to use the calculator. So on the calculator, I'm going to have a graph, and then I'm going to end up with a line, and I want to figure out this intersection. So I'm going to go ahead into y equals, I should have left that, 2 to the power of x. And then in the second one, I'm going to do 10,000 thirds. I'm going to graph it. Oh man, 10,000 thirds. I probably need like a higher window, right? Oh, sorry, I need to change my X window now. I can now see my Y. So let's see, let's make this max. What is it right now? It's 10, let's just make it 50, and I'm hoping that will work. Yeah. So I want to figure out that actual point of intersection. So let's go ahead with second trace intersect. And let's move the cursor. You can see where my y value is, or is it? No, maybe my y value is way too high because it has like an e in there, so it's a huge y value. There we go. So you can kind of see pretty close. I'm going to push enter, 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 and it's 11.7. And we were dealing with, what were the units? So 11.7. We said that our units were minutes. So that's how long it will take, based off of this information, for there to be 1 million bacteria. What about this one? How many bacteria will be present after 5 minutes? Well, that's an x value. So I can go ahead into the equation we wrote and plug in 5, right? So I can look at the table of values and figure out where x is 5. Oh, 32, right? So at 5, no, just kidding. It's that one over there. No, it's not. It's this one. No, it's neither. I don't have it plugged in yet. I didn't have it plugged in. My fault. 300 times 2 to the power of x. And then I can look at the table of values and look at where x is 5. And I'm going to see that it's 9,600 bacteria. Right? Or maybe I'm just going to do 2 to the 5th times 300. I don't need to do it in the table of values. But showing that what is happening and then making sure that you're including labels units is important. So let's look at the second one. So a certain radioactive material's decay is modeled by this function. We have not looked at E yet. E is Euler's number. It's kind of like pi. It's an irrational number that it's very commonly used. So we haven't looked at it, but it's going to work the same. It's just an irrational number. It's like using pi. It's about 2.71. So 750 e to the power of negative 0.2t. Oh, if you have a negative exponent, keep in mind that's going to be decay, right? Because that's like saying 1 over e, where it's measured in days. How many grams are there originally? So that's the starting. If we know how the formula works, that's like saying 0. So when t equals 0, r of 0 is going to equal to 750. So 750 grams is the starting amount. Find the amount of material remaining after 2 days. I actually wonder if did I start on the wrong page? It's okay. Did I? I might have. It's okay. Find the amount of material remaining for after 20 days. So I didn't actually start with this. X is the number of days, or I guess that's probably t. So t is the number of days, and r of t is the amount in grams of radioactive material. So we're going to write a particular, we have the equation. So find the amount after 20 days. I have to put where t is 20, right? So you're trying to find r of 20 equals 750 e to the power of negative 0.2 times 20, right? And then in our calculators, and this might be your first experience or exposure to using e in your calculator, so this is important. 750 for e, I'm going to do second, and where you have that ln button, and it's going to do that. And some of you guys, if you have a different calculator, it's going to create the little caret, and you just want to make sure you're changing it. negative 0.2 times 20. And maybe you need to close, maybe I need to add, I'll add in some parentheses. Negative 0.2 times 20, close them, enter. So I get 13.737 grams, right? And it's going down, it's decaying, so that makes sense. It should be less than what you started with. Find how many days have passed when 1/3 of the material is still radioactive, right? So a third, so if you started at 750, a third of that, 1/3 of 750 equals what? 250. So when that's going to be your R of T, right? So you want to know, well, 250 equals 750 e to the negative 0.2 t, right? So I'm going to divide by 750, and then watch this. Oh, look, that's just a third, equals e to the negative 0.2 t. And this is where I'm going to, just like we did above, I'm going to go back into the calculator. Y equals, one of them is going to be 1/3, and that's going to give me a line. And I'm going to have e, second ln, to the power of negative 0.2 x, which is t, and graph it. I might have to change the window again. Probably. I'll do zoom 6 to get it to be standard again, and then see what I need to do with that. Oof, that's me. I might need to zoom in a little bit. Let's change the window. I probably don't need this. I'll make it 0. This window, probably don't need it to be as big. Really zoom in on that. So that's the line I'm working with. Let's see, can I see it cross? Oh, yeah, right there. A little hard to see. So second trace intersect. It's around there, so I'll do enter, enter, enter. So, yeah, right? So that's 1/3, so about 5.5. 5.5 days. Or 5.5 days. Right, so I found their intersection. Awesome. So I think you guys are actually going to be flipping back a page. I believe I went slightly out of order. Actually, I'll keep going and then I'll go back to where I was supposed to start. My fault. So now that we have the general idea, let's see what we can do with these next two. So the number of strep bacteria in a controlled colony is found to triple every minute, right? So that means now your growth rate, your B, is going to be 3. Sorry. If there were initially 200 bacteria, that's your A. In about how many minutes will the bacteria be 500,000? So we've got Y equals 200 times 3 to the power of X. And we want to know 500,000 equals 200 times 3 to the power of X. Divide by 200. Divide by 200. So I'm doing 5,000. Half of 5,000 is probably 2,500, right? Yes. 2,500 equals 3 to the power of X. And then I'm going to go ahead into the calculator because I don't think I can do anything where I'm going to get 3 to no power. I don't think is going to give me 2,500, right? No. I'm just going to, okay. So Y equals 3 to the power of X and 2,500 And let's do zoom 6, then we can change the window base off of that. We're definitely gonna have to make the window larger, right? Because we need to go to at least 2500. So let's make the window, the Y max, go to 2600, and let's make this X max go a little bit more. Oh, there it is. Right, so I want to find their intersection. So second trace intersect. X is 20 right now. And the Y's are pretty big. So I'm just looking there and I can see how large those Y's are. I need them to be a little bit closer to 2500. So probably, can I see it yet? I'll probably go with about that. There you go. So 7.12. So how many minutes? X is going to equal about 7.12 minutes. And we will learn another method to do this using logs, but we're just focused on X minutes right now. And then how many bacteria will be present after 8 minutes? So Y equals 200 times 3 to the power of 8. I could type it into Y equals, or I could just do 200 times 3 to the power of 8. And I get this number. So let's see. Comma, I get 1,312,200 bacteria. Right? It's got to be more than the 500,000, right? It's longer. So evidently longer, and since we're growing times 3, that's what's going to happen. Great. Okay. So a certain radioactive material, decay, is modeled by this equation. So you see E, you see Euler's number again, where T is measured in days. How many grams are there originally? When T equals 0, R of T equals 620. So originally, 620 bacteria. Right? It says to justify, there's my justification. When the time is 0 at 0 minutes, or the 0 days, I'm sorry, there are 620 bacteria. Find the amount of material remaining after 10 days. That's I'm finding R of 10 equals 620 e to the power of negative 0.3 times 10. I'm actually going to see what is negative 0.3 times 10 equal to. Negative 3. And then that's, I didn't need to do that, but I figured why not. And then I'll go ahead and put this into my calculator. 620 e to the power of negative 3. Whoops, me error. E to the power of negative 3. 30.868, 30.9, I'll say. There are going to be 30.9 grams. Right, that makes sense. It should be decreasing. So after 10 days, there should be a lot less. Like, think it was like cut by e to the power of 0.3 each time. Find the half-life. So this is like how long before half is left, or it's still radioactive. So let's see. Well, it started at 620. So let's see how long does it take for it to get to 310. Right, so 310 equals 620 e to the power of negative 0.3 t. I divide it by 620. This should look familiar from the other example we did like this. And then I'm going to go ahead and I'm going to find your intersection in the calculator. The algebraic piece again will come later for us. So half e to the power of negative 0.3x. And we'll go ahead and graph it. I might need to change the window. Probably do. I should have done zoom 6 to see what happens. Right, and then I might need to zoom into some. I might be okay. Second trace intersect. I could zoom in a little bit if I wanted, but I can see that. Let's get close. I think it's around there. So at 0.5, so 2.31. So 2.3 days. Awesome. So we're going to go back to actually the first page that covered this content where it said exponential modeling, because I accidentally skipped that, my fault. So join me in that. And if at this point you want to pause the video and you want to try this on your own, I encourage that. I think that's a fantastic idea. So you are a mathematician for a major movie company. You are figuring projected cost for their newest movie that is currently being filmed. You find out that when filming started, $1.6 million had already been spent, and then after 2 months, this is starting, after 2 months, $5.4 million had been spent. Assume that the cost of the movie varies exponentially with the number of months it takes to film. Define the variables and given points and write the particular equation that models this situation. So independent, or your x, is going to be the number of months. Your dependent, or your y, is going to be the amount spent in dollars, right? Or is it going to be millions of dollars? Yeah, maybe we should say millions of dollars. The points we know are going to be 0, 1.6, and 2, 5.4. So we can use some of the stuff we did where we had to figure out a particular equation. We know what A is. Y equals 1.6 times b to the power of x. We just don't know the growth rate. And then I can plug in this other point. 5.4 equals 1.6 times b squared. Hopefully we're seeing some connections. Divide by 1.6. What do we get? 5.4 divided by 1.6 gives us 3.375. 3.375 equals b squared. We can take the square root. And I guess I'm going to have to round this. Right? Yeah, I'm going to have to round this. It is 1.84, I'll go with 1.83784. Is the growth rate, approximately. So the particular equation is going to be y equals a, which is 1.6, b, which is going to be 1.84 to the power of x. Right, so I did all 3 parts. I defined the variables, I wrote down the points, and I wrote the particular equation. If it took 5 months, that's an x value, to film the movie, how much did it cost to make? So y equals 1.6 times 1.84 to the power of 5. And remember, we're doing it in millions of dollars. So you've got 1.84 to the 5th times 1.6. I got $33.7 million. Predict the cost of the following movies given the time it took to time them, to film them. It must mean film. My fault. So 7 months. Do you like that? American Pie. If it took 7 months. So y equals 1.6 times 1.84 to the power of 7 for this one. And then for Transformers, hopefully we got that too. Y equals 1.6. It took 1 week. 1.84. Well, X is in months. So we're going to assume that there's 4 weeks per month. So this is going to be 1/4. Right? You're going to be dealing with a fractional exponent there, like the 4th root. So let's see. The first one, 1.84 to the power of 7 times 1.6. I got $114.2 million. And for this one, 1.84 to the power of 1/4 for the 4th root times 1.6, I got $1.9 million. So finally, if Dipsy Doodle, doesn't make sense to you guys yet, cost $25 million to film, so now we're giving you a Y value, an outcome. How long did it take to film? So 25 million equals 1.6 times 1.84 to the power of X. So let's see, divide by 1.6. 25 divided by 1.6. 15.625 equals 1.84 to the power of X. Let's go ahead into our calculators. Y equals 15.625 divided by 1.84 to the power of X. We're going to find their intersection. So let's let them graph first, see what plan I need to do to change the window. Okay, so I can see that. Will I be able to see the 15, or do I need to change the window a little bit? Right, so I'm probably going to change it to like 18. There we go, now I can see it. Awesome, so second, trace, intersect. Let's move it over to there. Let's see the Y's. So 4.5. So about 4.5, we defined it in terms of months, so 4.5 months. So if you notice, like I'm having you guys divide by this number and not just enter it and trace it as is, because it is going to lead to something we will do moving forward. And so I think it's a good thing to practice and know right now. So to summarize what we just talked about, and this was just, we just looked at the modeling piece of this. So we applied our knowledge of exponential functions to real world situations involving growth and decay. So if you have any questions, let me know. Otherwise, keep practicing and keep watching. Thanks.